Hi everyone, welcome to this XAI seminar. Today we got Zhijing, sorry for the pronunciation. She's a assistant professor at the University of Toronto and a research scientist at the Max Planck Institute in Tübingen, I believe, in Germany, working with Bernard Scholkopf. She's the founder of Eurosafe AI, as well as a Cypher AI chair and a faculty affiliated CHAI at UC Berkeley, as well as the member and faculty affiliate of other institutes, as well as an Ellis advisor. And a research area are large language models and causal inference and responsible AI. And she's going to cover, together with Abir, student, a series of works working towards causal mechanistic understanding of LLMs. So very much looking forward to your talk. And first floor is yours.
Thank you so much for the warm introduction. Great to be here. Today we're together giving a talk on towards a causal mechanistic understanding of language models. So the main outline is that in our talk, we will cover that behind all these impressive LM performance, what is the motivation for interpretation? And when interpreting them, how do we understand both their behavior and mechanisms and the potential studies that we will cover, including circuit-based discovery of LLMs, and also comparing it with probes, as well as training data attribution. So starting with the motivation, LLM seems to be impressive at many tasks. That include their mathematical skills, as they have continuously increasing skills across different benchmarks and the capability dimensions. And also the coding performance of models have been really impacting every computer scientist. Similarly, we also see the so-called reasoning skills over images and structures. And why do we need to study interpretability, and what does it enable us? So we are deploying models that we do not understand from a lot of quotes from Dario or Jeff. Especially like Jeff mentioned, I'm very concerned about deploying such systems without a better handle on interpretability. I consider it basically unacceptable for humanity to be totally ignorant about how these models work. So there are both negative concerns about if we don't have full understanding, then the deployment is risky, and then positive aspects that constructive aspects that we should add safeguards to give performance guarantees or limit risks. And these safeguards can largely be interpretability inspired. So in terms of the levels of understanding that happens within models, the first level is associational, which means observe potential correlations in the model. That happens with, let's say, we checking what type of inputs activate what type of attentions. And that's like the very early work also across computer vision and many other machine learning tasks. And then recently we have also seen tools that looks at the activations such as logit lens and so on. And then also, of course, on the activation space, people can further train probes that classifies this representation state to certain properties in the data. And then the second level is interventional, namely what Julia Paul calls like the run two in his causal hierarchy. So basically, it means that we can perturb or manipulate components in the neural network that highlights the causal effect of certain neurons or certain features to the model response, as well as, and then the methods can be causal ablation and patching, and so on. And then the last run in Judea Pohl's hierarchy of causality is counterfactual, namely reasoning about alternative internal computations, what would happen under different mechanisms of the model. And then to enable counterfactual reasoning, we actually need to grasp the full causal mechanisms, and namely a mechanistic explanation to identify the internal computation responsible for a behavior and predicts how interventions will change it. So an example of this mechanistic layer is the measuring the progress of grokking by Neil Nanda, where there is actually a deep enough interpretation about how modular addition could be done in transformers. So now we look into how are capabilities represented in language models. And we'll basically map a couple of our lab's research output to these 3 runs of causality: associational, interventional, and counterfactual causality. We'll first start with the preliminary of mechanistic interpretability and the linearity hypothesis. So the core assumption behind a lot of interpretability work is the linearity hypothesis, that the concepts are represented as directions in high-dimensional space, and semantic relationships manifest as linear transformations. So from the very early word to vec and the glove time, there is this famous world vector study that contrasts the difference between man and a woman is the same as the difference between king and a queen in the vector space. And then this is sort of an inspiration that if we find these directions, we can read the model's mind and mechanisms when it applies to, let's say, the residual stream of the LLMs. And then moving further, there are many work that test for correlation, as we highlighted before. So let's say that if the data that is positive sentiment is all represented as the blue dots, and then the data for the negative sentiment is all represented by the red dot, then a decision boundary of that in the representation space can then be used for linear probes to understand what explanation it is in the representation space to classify, let's say, the sentiment of the text. It can also be of many other nature that you can attribute a label to the data and then interpret it. And then one of the method here is logit-lens, namely, not only can you train probes, but also from the representation space, you can attach the vocabulary embedding matrix to further understand at this point what vocabulary distribution there is in models generation process. So one of our early studies in mechanistic interpretability is the work on competition of mechanisms, tracing how language models handle facts and counterfactuals. So the motivation we have is the inverse scaling price, where we find an important task where larger LMs do worse. So one such task is redefinition. So in this inverse scaling price organized a while ago, some example prompts is redefine pi as 500, then what is the first digit of pi? Then the correct answer is 5. So similarly, in our framework, we also compose systematically a lot of such redefinition tasks, such as redefining code blue as a technical, redefining code blue as a technical fault in our emergency code, but not a medical emergency. And then now asking the model, what does code blue mean? So what is happening here is that there are two competing mechanisms, one being the memorization from training data, that the model is tempted to recall that code blue refers to medical emergency, given its pre-training. And then the second mechanism is the redefinition that we give in the context. So another way to interpret it is one is weight-based model memory, and then the other is context-based, either memory or suggested computation. So in the above case, the LM fails to understand which mechanism it should let win. And we do generalize it to many different cases as well. So some other applications could be competing redefinition. One is defined earlier, and the other is redefined later, still in the context. Or knowledge update, which is very relevant for temporal language model responses. Let's say the change of country leaders after every term should be such of an update. And then one of the explanation framework here is that we have put the sentence input in this format, like now we redefine iPhone being produced by IBM now, and then ask the model again, iPhone is produced by what? So we do see that in early layers, like MLP layer 0 or attention layer, there is a knowledge recall mechanism that connects Apple with iPhone. And using logit-lens, we see that the probability of iPhone is really high when associated with these tokens. And then, however, there is also an induction circuit elicited by the redefinition. So the word IBM has been also elicited in the attention layer 5 to 8 and 11. And then the effect of all of them have been fed back to the residual stream and affect the final logits. So then the success of the model is basically on whether its prediction is more influenced by the induction circuit or the knowledge recall circuits. So as we have seen that it's when we mention the competition of mechanism in this case, it's more about after the logit-lens projection, what is the probability distribution evaluated on the point IBM and then the point Apple. So we do plot some example numbers and show that in the last several layers, when the model do it correctly, the token IBM was promoted to the argmax across the distribution of vocabulary. Then we also tried varying the input, and although the original word is Apple, we can not only replace it with IBM, but also Snapchat, MSN, Face, environment, and so on. So these are the cosine similarity of the alter token and the original token. And then we saw that by different models, the frequency of the winning mechanism basically decrease according to the model size, roughly. And then, like, we in general see that the larger the model is, the stronger the memorization circuit it has. Following this, we have applied the same idea of the competition of mechanism to vision language models. So we handle the knowledge conflict in VLM, such as if you have both an image and a text conveying different information, then how would the model resolve the conflicts? So we applied a similar framework to see and also validated it across a large set of data from taking the WHOOPS dataset, image only, and create, transcribe the captions of it, then change the key content of the textual information. So I probably skipped the details, so we have more time going through the causal circuits study in our lab. The main methodology is similar. And then the last study I will present in the steering vector branch is the reasoning memorization steering. So we basically found the steering vector that controls the extent of memorization skill and the reasoning skill in LLMs, and basically conduct two different data sets, one on memorization and one on reasoning heavy tasks by taking existing benchmarks and separating them by the level of memorization needed and reasoning needed. And then we use the linear reasoning features by taking the difference in means across these two corpora. Then I'll just quickly skip through. So this is a basic dataset composition. And then we quickly go through the results section. So there are two types of results. The first one is that when we visualize the representation using TSNE in terms of whether it is reasoning heavy or memorization heavy, they do show a clear separation. And then further, we have the steering vector basically learned from these representation differences. And then we show the causal effect of intervening the representation by such steering vector by quite significant boost. Let's say on memory intensive data sets, we push the representation on the memory direction and lead to increase such as 7%, 12%, and so on. And then on the reasoning data set, the really large increase is on llama 3, 8 billion, we lead to a 9% boost, and gamma 2 has a 15% boost of performance. So this is our work that we have done on the correlational representation space interpretability. And however, the linear probes alone are not enough. So I'll give it to my student Abir to go through a set of continuous work on mechanistic understanding of the models.
Yeah, so let me take it from there and share my screen. Yeah, so as Zhijing said, linear probes alone are not enough, and this is for several reasons. The first one is that high-dimensional representations are, by definition, easily linearly separable. So even for random labels, we would get linear probes that would have very high accuracy, and this would mean nothing, basically. Also, it was shown in this work that probes can detect information that is not causally used. And by this, I mean that if we remove the direction that the probe learned, then this would not affect the prediction of the model. So actually being decodable, i.e. detectable by a linear probe, does not mean that the concept is used or that it's real, that it's basically represented. So this hints at the fact that we need to recover features that the model actually uses. And one candidate for this is neurons, but then neurons suffer from the superposition problem because we basically have less neurons than the number of concepts to be represented, so models default to superposition. So it would be great if we could disentangle these representations that the neurons give us. And one solution to this is SAEs, or sparse autoencoders, which is like a family from dictionary learning. And the idea with SAEs is that we want to project our representations onto an overcomplete basis so that we achieve entanglement. And we want this representation to also reconstruct the same thing as the original representation, but to be sparse, which means to be entangled. And SAEs have been used repeatedly with different setups, and they have shown like a good performance. The problem with the SAEs is that they only kind of decompose our representations, but they don't give us an idea of how the computation inside the model is done. And such a question could be answered by transcoders, for example, where instead of, for instance, projecting an MLP representation onto an overcomplete basis, we would project basically the computation between the two such that we have something like this. So we approach the computation done from MLP using our new network that is both sparse and faithful to the initial computation. Again, the problem with both SAEs and transcoders is that they are in some sense static, and they don't give us a picture of how these features evolve across layers and how each one influence the others. And this is where cross-layer transcoders were introduced last year by Anthropic. And the idea is basically to have to have a model that mimics the initial or the original model, but that is more interpretable and sparser. And they achieve this by basically doing just like SAEs, projecting each representation onto an overcomplete basis. But the tweak here is that the reconstruction of each representations given by all the previous representations from the previous layers, as we can see here. Again, we have the reconstruction laws to ensure fidelity and sparsity, but the innovation here is that we kind of have a new network that mimics what the initial model does while being sparser and more entangled. And cross-layer transcoders were introduced last March, or like March of the last year, but there were no open source implementation of them. And that's where CLT Forge, our library, comes. It's an open source, scalable library that enables training of cross-layer transcoders end-to-end and generation of attribution graphs and the study of these. You can find CLT Forge here, and the pipeline summary is as follows. So CLT Forge goes from the saving of the activations to the training, to the auto interrupt generation of the features, to the attribution graph, and finally to the visual interface. And just some technical details here. So the library supports both on-the-fly activations generation, which means that we don't store activations, but we generate them on the fly if we're short of storage. And it can also support a pre-generated option where the user can pre-generate the activation to avoid any on-the-fly processing. And we also support quantization and compression of these activations so that we reduce the high memory usage required. And we can achieve up to 12x reduction while only having 2 to 3% reduction in activation reconstruction. And with the library, obviously, we can train CLTs, and we can actually train them on big models, thanks to the feature sharding implemented. We can generate auto-interp and attribution graphs based on the CLTs and our models, but also the auto-interp that we use for the visual interface to basically use the CLT and kind of inspect the features and the relationships between them. We use this library to conduct a set of studies inside the lab. One of them is understanding the multilingual representations in LLMs. As we all know, there is this multilingual performance gap where English performs better than the other languages, despite the fact that most of the world population uses non-English as a primary language, and that the fact that non-English languages still struggle can cause like unsafe behavior and safety issues. Prior work has tried to understand how this multilingual processing happens inside LLMs, and the conclusion was kind of similar in the sense that models in general use or process non-English inputs by routing through English representations. So long story short, models in general use English representations to process non-English inputs. But there is something that feels wrong with this in the sense that if this is true, then how would we explain the fact that English is better than the other languages? So if all the processing is done in English and the model just translates back to the original language, then where the problem comes from. So in this sense, what the previous work has done is kind of limited in the sense that only logitLens were applied, and logitLens give us no clue about how the features interact with each other, which is interestingly what cross-layer transcoders provide. So in the following, we will try to address each of the following questions. We will try to understand if LLMs really think in English, and how do models handle language in general, and we will try to understand why do models fail in non-English languages. So to answer the question of if LLMs really think in English, we kind of constructed our own data set and trained our own models with different language distribution. We tried to vary the amount of English in each of the data mixtures, going from 90% for English and the rest for the others to uniformly distribute the amount of language per language. And we defined a multilingual score to be the entropy over the probability of a feature belonging to language. We compute this using the following, where A is just the activation of a feature at a token for a language, and our entropy metric would basically mean something as follows. So if it's low, it means that the features are language specific, and if it's high, it just means that the feature is basically multilingual and that it kind of has the same probability over all the languages. Interestingly, we have found that across all the data mixtures that we have defined before, where we varied the amount of English, the entropy or like the kind of features that happen inside the model are kind of similar. So in the middle layers, there is the surge where we have more multilingual representations and a kind of shared multilingual space between all the models. And in the early and late layers, it's more of models using language-specific features to kind of process the inputs. But interestingly, even if we remove the English data entirely, we still see the same pattern. We still have a shared multilingual space in the middle layers. So apparently languages or LLMs don't think in English. And we have found that the same pattern kind of emerge even in bigger models, but that it needs kind of a minimal depth to kind of emerge. So we tried some tiny stories model with only 4 layers, and it failed to give the same pattern. We also tried this on several prompts, and we tried to analyze the attribution graphs, and the findings are the same. So in general, we have the same pattern as in early layers and late layers are language specific, and the middle ones are kind of shared multilingual features. We also find that for determiners, the circuits used by the model is largely language specific, and this has been like demonstrated in a previous paper. So that's good. We also interestingly found that for low-performing languages such as Arabic, they suffer from self-tokenization, as we can see here. So each word is sub-tokenized into many tokens, and this results in the fact that most of the early layers up to layer 3 or 4 is used just to reassemble these words rather than learn higher level meaning as it's done in other languages. So it's kind of that these early layers in low performing languages are kind of not used as they should be, and they're kind of wasted. The second question we had is, how do models handle language? And we found that there is a set of high frequency features that are active in the final layers. These features are language specific, and they drive the language. They're responsible for language inside the model. We also found that intervening on these features and removing them, like by zeroing them out and replacing them with features from other languages, results in the model answering in the language in which we use the features, even if the input is in English, for instance. So if we take the features responsible for English, we remove them and replace them with German features, then we would get this Zhijing, even if the input is in English. And these features, by the way, decode linearly from the early feature, from the features from the early layers. Now the question is, given all of this, why would models fail in non-English languages? To study this, we did this small experiment where we took our initial model, we fine-tuned it on the set of our underperforming languages to get like a fine-tuned model. And then we took our CLT and we also fine-tuned it to get a new CLT, and we fine-tuned it on the new model fine-tune. And the idea here is that if we push the model to do better on the languages it underperforms on, then the first things that it would change are the things that it needs the most. And the CLT would tell us what these things are. We found that the CLTs are our new CLT, the fine-tuned one, has like the most difference, or like the least cosine similarity in its final layers, meaning that the features of the final layers are the ones that undergo the most of the change, which is kind of intuitive in the sense that the model wants to strengthen these features so that it has even stronger connections to the multilingual shared space that we have seen before, and it can translate and map language-specific inputs to this shared high-level representations better. We also tried to divide the features into two buckets: the most similar, or like the ones that have undergone the least change with highest cosine similarity, and the rest. And we have found that in early layers, it's English, the feature changed so that English dominates, English and French dominates, and in late layers, it's more of the features. For example, if we fine tune on Arabic, then it's Arabic features that would change a little bit, but we would get more Arabic features, and that the rest would basically align. And yeah, so that's basically it. To like have more time for the other work, let me just skip these slides. Yeah, so we also use CLTs to understand how linear probes emerge, because basically linear probes are interesting. We have seen that they can help in some sense, but they're not decisive in the sense that they're kind of correlational, and having a linear probe doesn't mean that it's implemented somewhere, or that the concept is represented somewhere in the circuit, in the model. So we try to use CLTs to actually explain how these linear probes emerge. And the idea here is, if you remember, this is like what a CLT circuit looks like. And in general, here we just use the predicted logic to do the attribution. But we can easily replace the logit vector with any other vector. And for instance, we can replace it with a linear probe to understand how, or like what features influence this linear probe. So we did exactly this, and we found a circuit responsible for the linear probe. For a toxicity probe, we would find a circuit, and yeah, for all of these other probes. And the interesting thing is that we found that a circuit responsible for the probe doesn't influence the rest of the circuit, or the circuit responsible for the generation. So these are kind of causally separable circuits. We also found that the structure of the CLT graph predicts the probe quality, and that even like across prompts, even if we vary prompts and we keep the probe the same, or like the concept the same inside prompts, then the same circuits modulo some features would emerge. So yeah, this is like a meta-causal graph of a learned model that we like to use inside our lab, where we basically think of a model as a combination of these things, as a combination of training data, weights, activation, and output, and each one of these influence the rest, and each influence is basically something we study inside a group. So we have seen that, like, we have seen instances of mechanistic interpretability, and this kind of explains the link between weights and activations. Associational behavioral work would explain the link between activations and outputs, and training data attribution would actually explain how outputs are influenced by training data. So these are some works that have been done inside the lab, training data attribution wise. But before, let me briefly introduce like some of one of the prominent techniques used in training data attribution, which is influence function. So in general, in training data attribution, we have a model and a training data, and we have a prompt and a response, and we want to understand or identify the most influential training data for this particular model response. Influence function does something like it represents the test prompt as a test gradient, the training doc as a training gradient, and it uses the Hessian to actually do the product of these three components and have a rank over the training documents for the from the most influential one to the least influential one. So using influential functions, we have seen or we have found things like the test of time. So we basically found that the post-cutoff performance decay that was used to detect benchmark contamination is not the right way to think about benchmark contamination, because the contamination or the decay is not predictive of it. And we can completely remove or remove the decay by just replacing the retrieval-based question given to the model by questions generated by LMs on the same kind of documents. So the decay is not predictive. And we have actually used influence functions to kind of validate this and show that in the case of retrieval-based questions, so either closed questions or verbatim questions, the model actually uses excerpts from the training data to solve the problem, which shows like the benchmark contamination. But in the case of the LM generated questions, it won't, because the LM kind of shuffles the time structure. It was also used in this work to study the LM political propensities. And the general finding was that if we use n-gram retrieval and influence functions, then n-gram restricts the set of training instances that influence functions reasons upon, and this can result in biases in what influence functions find. So actually finding that something is not influential in this case does not mean that this thing is not influential. And we give an example of state-affiliated media here, where its influence is very low, but it's just because it's not present that much in the training data that the n-gram retrieval was blind to it. But if we add it to the corpus on which influence functions reason, then the influence would be higher, and that this is like different across languages. We can also use influence functions for things like the social harm bench, where we found that training data is behind like the most successful attacks. So if we analyze the weight-based tampering attacks, then we found that the documents linked to sociopolitically harmful responses are the ones behind the success of these attacks. So far, we have seen the use of influence functions, but we have gone a step further and we asked, what if we could use what we have learned from mechanistic interpretability to actually come up with a new training data attribution method? And this is what we have tried to do with this paper. We actually used steering operators to do interventions in the activation space or in the representation space of models to measure or to approximate training data attribution. So instead of going through the parameter space as I have showed you with influence functions and the Hessian, the gradient, etc., we can just perturbate by the steering vector and get an estimate of training data attribution that is actually as competitive as the other methods, and that is much faster, like 12 times faster or so. Activation methods can also be used to study things like chain of thoughts and the computation inside them, where we have shown here that the tokens inside the chain of thought are important and are causally meaningful, but models also rely on implicit computations not expressed in the trace. We have also shown in this paper that reasoning models, like the representations inside reasoning models are progressively refined. Yeah, and in this paper where we show basically like inductive biases like induced biases like psychophancy or other things in LLMs actually correspond to causal active directions in hidden states introduced during the alignment tuning, and that we can identify those and steer them to recover in biased behavior. So for future directions, I'd like to think or to say the following. So mechanistic interpretability is good, but as we all know, it's limited in the sense that the claims in general don't generalize. And the question is, how would we make them generalized? My understanding is that we would like the mechanisms we find using mechanistic interpretability to be identifiable. So we can actually identify circuits as we do with mecinterp, but we don't know yet if they are the mechanism or just a mechanism. So if we have a principal understanding of why mechanisms arise, then this understanding would reveal like the full equivalence classes of a class of solutions implementing the behavior. But this is not always possible. So in that case, if this is kind of difficult, then causality would be something to replace it. And causality could be a key to generalization if we're not able to have basically a principled understanding. And we can think of it as all mechanisms being something like this, and then the identified mechanisms that would, or like the right equivalence class of mechanisms that explain a given phenomenon would be this identified mechanisms. And this is what we really want to achieve. And we would only achieve it if we really understand what's going on. But then if this understanding is difficult to achieve, then causal mechanisms could help. And they intersect pretty well with what we want to achieve, better than correlational studies. And this is like a line of work we're working on in our lab. So thank you so much for your presence and attention, and feel free to ask questions. Thank you.